This tutorial we're going to be looking at the power rule as it applies to taking derivatives in calculus. Just to remind you, the power rule itself is written, there's a number of ways to actually write it, but let's assume that we're starting with, if we have the expression y is equal to x to the power n, then the power rule tells us that y prime, the derivative with respect to x, is equal to n x to the power n minus 1. So we take the value of the exponent and we bring it in front as a multiplying constant, and then we subtract 1 from the exponent. The best way I think to illustrate this is with some examples. So I'm going to go through a number of scenarios introducing the power rule. So let's start off with our first example, something very simple. Y is equal to x cubed. So this one falls into the trivial case for the power rule. So when I take the derivative, when I take y prime, take the derivative of this one, it's going to take this exponent and bring it down front as a multiplying constant. And then we have x to the power 3, but we have to subtract 1. And so my final answer for this one is going to be 3x to the power 2. So x cubed becomes 3x squared. So that's a pretty simple example. Let's take a look at one that's a little bit more complicated, but not terribly so. So we start off with y is equal to 5x to the power 4. Now this one, the presence of this constant in front, the 5, causes some people some initial confusion. And so you need to understand that all of these derivatives, when we talk about taking the derivatives, the power rule, and when we go on to other rules such as the product rule, the quotient rule, all of these are based on our definition of a limit. So this, for example, the slope of a tangent is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. And when we looked at limits, or hopefully you have looked at limits, if you had some constant multiplying by your limit, well, the limit as h approaches 0 of this constant value k is unaffected. The limit doesn't actually affect the constant itself. So another way of writing this is to take that constant k out as a multiplier and then write the whole thing. So I'm going to write it like this, and then that is the limit as h approaches 0 of f of a plus h minus f of a divided by h. And by doing it this way, you can see that taking the limit of the whole thing is the same as multiplying by the constant k and then just taking the limit of this interior part. Well, a similar rule applies because derivatives come from these definitions of limits. So in this case, when I take the limit, I actually write this now as y prime. Actually, let's use a different notation. There are multiple notations that we can use for taking limits. So here I've used xy notation to write my original expression. So I'm actually going to write this one as dy by dx, which is the differential of y with respect to the differential of x, which is essentially saying the derivative, is equal to the number 5 does not change. It actually comes out in front. And then we take the derivative of what's left behind, which is this polynomial x to the 4. And so what we get from that is we get 4, which is the value of the exponent. We bring that out front as a multiplying constant. X to the power, and then 4 minus 1 is equal to 3. So you can see that we just ignore this 5. The 5 stays as it is, comes out front, and then we take the derivative of what's left behind. And then to simplify this, I'll just move this page up a little bit. To simplify this, we express our final answer. 5 times 4 is equal to 20, x to the power 3. So let's see if I have enough room on this page to do this last example. Sure, I do, lots of room. And so let's look at another example. And this one is, I'm going to write this one using function notation. F of x is equal to, and this time I'm just going to give a quadratic in standard form. So 3x plus 7x minus 5. So for this one, when we take the derivative, we're going to make use of a couple of rules here. So let me go ahead. In this case, I'm going to take the derivative. So I'm going to say f prime of x is equal to, now, the first case we run into with this term, the first term, 3x squared, that's similar to this 5x to the fourth that we just did. So we're going to handle this in the exact same way, which is we are going to keep the 3 as it is, but then we are going to multiply that by 2x to the power, 2 minus 1 is 1. Then we add to that 7, and then we're going to take the derivative of the x. Well, what is the derivative of x? That is 1x to the 0. Where does that come from? Well, the exponent on the x here is an exponent of 1. So that exponent 1 is what comes here. That's where we get the constant. And then this value 0 is 1 minus 1 is equal to 0. And then finally, we end up with minus, and the derivative of the number 5 is equal to 0. So I'm making use of a couple of things there. First of all, the derivative of a constant is equal to 0. So the derivative with respect to x of some constant value c is equal to 0. You can see I've switched notations again. This is known as Leibniz notation. So this one is a constant, because a constant doesn't change. And the derivative is telling us the rate of change. So of course, the derivative of a constant is 0. And now the other rule I'm making use of here is the idea that if I'm taking the derivative of this whole thing, how can I break this up into the derivative of individual parts? And again, that comes down to the limit notation, which is if I take the limit of these multiple parts, then that is the same as, let me maybe write this out. I'll just split this up a little bit. So I'll write, I'm adding a little bit of a break here, and then I'm going to just write out the fact that the limit as h approaches 0 of f of x plus g of x, that is the same thing as the limit as h approaches 0 of f of x plus the limit as h approaches 0 of g of x. And if you go look up some of your rules or definitions of limits, you'll find all of these things are referred to. So basically the sum of some limits is the same as the limit of a sum is the same as the sum of a limit. And since our derivatives are from first principles defined using limits, then the derivative of a sum, which I've got here, is the same as the sum of the derivative, so I can break that up. Anyway, one last step here. Let's take this down and finish it off. F prime of x, just in a fully simplified form. We've got 3 times 2 times x to the 1, so 3 times 2 is 6. And x to the 1, we wouldn't normally write the x to the power 1, so we just write that as a 6x. We've got 1x to the 0. Well, plus 7 times 1 is simply 7, and x to the 0 is equal to 1. And again, we wouldn't normally write that, or we would multiply it into the 7. And the same thing, we don't normally write the 0, so we end up in this case with the derivative is 6x plus 7. So there are some examples where we're using, and these are all polynomial terms. We dealt with integer exponents, pretty simple. Let's go on to another page and look at something a little bit more complex. So let's take a look at example, I'm going to say example D. And this one is, let's go back to xy notation. Y is equal to the square root of x. Now, if all you're doing is the power rule, you haven't learned how to deal with this yet. So the first thing we actually need to do before we take the derivative is we're going to need to rewrite this in some sort of x to the power. So we want y equals x to the power n, or some form of that, or a constant in front, something along those lines. So how do we do this the same way? We use our understanding of radicals and fractional exponents. So I'm actually going to rewrite this as x to the power 1/2. And even though this is not an integer exponent, the power rule can still be applied to it. So I actually now can write this as y prime is equal to, and what do? I take the 1/2 down to here, and then I write it as x. I write it as x to the 1/2, and then I have to subtract 1 from that exponent. And then when I write this out, I end up with 1/2 x to the power 1/2 minus 1 is actually negative 1/2. And so I continue to work with this, so I get 1/2, and then x to the negative 1/2 is the same as 1 over x to the positive 1/2, which is the same as basically what I have here is 1 over 2 times the square root of x in the denominator. And if we want to show good form, we want to rationalize that denominator. So I'm going to multiply top and bottom by root x, and I end up with root x in the numerator over 2 times root x, which is simply times 2x. So if all you're asked to do is to take the derivative itself, well, taking the derivative, that's basically here. But to simplify it and leave it in a good form, that would be this one. So this one is simplified and in proper form. Okay, and finally, one last example, and I'll wrap this up. So we should have lots of room left on this page to do this next example. And so I will put in example E, and this one is going to be a combination of what we've seen before. So I'm going to say f of x is equal to, I'm actually going to write out I'm going to use the same polynomial quadratic that we used before, and I'm going to just throw an extra little twist in there, which is I'm going to put this whole thing over the square root of x. Now we definitely haven't learned how to deal with this, so what we need to do is we need to get this into the form of, again, we need something in the form of x to the power n, or a constant times x to the power n. So the way we do it is the way we started with the last example, which is I'm actually going to write 3x squared plus 7x minus 5. And the square root of x I'm going to write as x to the 1/2. Well, that still hasn't solved my problem, but you need to understand that this denominator applies to each of these terms. So I can actually separate this out to be, so this is the big step. I've switched colors here to show that this is 3x squared over x to the 1/2 plus 7x over x to the 1/2 minus 5 over x to the 1/2. And by writing it this way, I can now actually take care of these exponents, because I have a 3x, 2 in the numerator and a half in the denominator actually gives me 3 halves, 2 minus a half, plus 7 x to the 1 over x to the half, 1 minus a half. I'll put a 1 there just to, so there's 1 minus a half. That gives me x to the power negative 1/2. Sorry, no, that's to the positive 1/2 this time. And then on this one, minus 5. Well, x to the 1/2 in the denominator becomes x to the negative 1/2 in the numerator. Now I actually have something where I can take the derivative. So let's go ahead and do that. F prime of x is equal to, and so we are going to take the 3 out, and then we end up with 3 halves x to the exponent. 3 halves minus 1/2 is 1/2, plus 7, and then I take the derivative of this variable term. That's going to be 1/2 x, and 1/2 minus 1 is to the negative 1/2, minus 5, and then I take the derivative of this one, which is going to be negative 1/2 x to the, and now negative 1/2 minus, I'm just going to illustrate that one in a little bit more detail, negative 1/2 minus 1 is equal to negative 1/2 minus 2 halves equals negative 3 halves. So this is going to be to the negative 3 halves for that exponent. And having done all 3 of those, we could simplify and we could deal with these exponents and write it in a new form. I'm just going to do the very basic simplification right now, which is to deal with the constants. So 3 times 3 halves is 9 halves x to the 1 half plus 7 halves x to the negative 1 half minus we have two negatives here, so that's actually going to become plus 5 over 2 x to the negative 3 halves. There's more simplification you could do for this one, but I'm going to leave it at this point. We've taken the derivative, and I've shown you how to deal with when we have a single term, which is known as a monomial. So we have a monomial in the denominator. If we had a binomial or higher order term in the denominator, or with more terms in the denominator, we couldn't do this. But with a monomial there, we can actually break it out into individual terms and still apply the power rule. Okay, I hope that provided some clarification on how to use the power rule in various situations.